like this. So this part here is going to go something like that, right? And that turning down is going to kind of turn up. So an odd function will be symmetrical about the origin no matter how weird it looks on one side, it will look similar on the other side. Okay? So obviously, I don't know what the function would be here, but it would be odd. All right. So again, we are still kind of doing review and preview of chapter 5 here, but we're going to move into 5.1 here shortly. So any final questions about that symmetry? Okay, so the question was asked, is there a function that is neither odd nor even? And I want you guys to take a minute here and see if you can come up with one. Would it be something without an x value? Well, why don't you try and create one and prove it to yourself, and then let's see. So if we have a constant function, yeah, if that's what you mean, y equals 5, there is no x value. So is that symmetrical about the origin? No. Is it symmetrical about the y-axis? Could, yeah, it could. You could say this is symmetrical about the y-axis. This is the exact same as that, I suppose, right? But think about something else. You know, this might be even. Would it be odd? I don't know. If you rotated around the origin, would it be odd? So if you rotated this around, you know, would you be able to get, you know, this mapped back onto itself? I don't know. It's a good question. Okay, but let's stick with ones that have variables. So this is even, we know. Okay. What about something like this? Is that odd? If you add something like that. Now you know what this looks like, parabola, right? It's a parabola. If you graphed it, like I'm going to do here, then you might be able to tell, you know, if you can find any symmetry, you might be able to guess. So without even substituting any points here, let's just try this. X squared plus 3x. We'll graph that. Okay, does that look like it's symmetrical about the origin or about the y-axis? Okay. Doesn't look like it's symmetrical about the y-axis because the vertex is over here. Origin, does it look the exact same on this side of the origin as over here? No. So try. So try x equals -1, see what you get, and x equals +1. See what you get for a value. All right, so if we look at this here, fill in these values, we get y equals -2 for a -1 value, and if we do the +1 value, we get 4. So that is neither the same number, just different sign, nor is it the exact same number. So yeah, that would be, there's lots of functions that have no predictable symmetry about the y-axis or the x. But if you happen to come across you know, something that is odd, then you know it has some symmetry, or is even has some symmetry. Good to go? All right. Keep hitting that desktop icon. Next page. All right, so 5.1. Okay, we're actually into the textbook here now. None of this review, preview stuff. Vertical, we're going to do kind of a combined lesson on vertical and horizontal asymptotes. So let's do it kind of, 5.1 is vertical asymptotes. And I will spend a little bit of time just doing vertical asymptotes, but like I say, it's not probably going to be a whole class worth here. So vertical asymptotes. What do we know about vertical asymptotes? Can anyone tell me what we know already about a vertical asymptote of a function? What does it look like? How do we know we have one? Etc. etc. Anybody? Okay, so if the graph approaches positive infinity on the y, you kind of drew this with your finger, sort of like this, and then comes down from negative infinity like that. Is that what you drew with your finger in the air there? Okay. And so where's the asymptote in this whole deal? Okay. All right. The asymptote is not actually defined. Good, good. So at this x value, let's say, we would represent it with a dotted vertical line, right? And you're right, that would be part of the domain that is undefined. Okay, and this x value causes a vertical asymptote. Yes, so if we're looking at a graph, that's what it looks like. It's part of the graph, y, where the x value causes the y value to be undefined. Okay? What does that look like in an actual function? So y equals, can you give me a function that would have a vertical asymptote? A rational function, okay, you're getting warm. Yeah, what kind of rational function? Or can you think of an example, something simple? 1 over x, okay. So you're saying this has a vertical asymptote, okay? I would agree. Now, why does this have a vertical asymptote? Finish your thought there. Exactly. There's values of x that would cause the function to be undefined. And that's exactly what we drew over here. And so, obviously, if x was equal to 0, y would be 1 over 0, which is a problem, right? That's bad, okay? So that would be undefined. So at x equals 0, we have an issue, and we would have a vertical asymptote. So if we kind of get rid of this, okay? And let's not get to the graphing calculator here right away, okay? Let's just pause on that, because that's kind of the easy way out a little bit. If I was to graph this, let's say, because this is what we're working on this chapter, right? We're working on graphing this stuff without technology. So I know that I have a vertical asymptote at x equals 0. That is true, absolutely true. So put a little dotted line there on the y-axis for the x equals 0. So what kind of values, where are my dots going to be? So am I going to have like dots here or over here? Like where are these points going to be? And if we think through this rationally, which this section actually just asks us to kind of do that, there's no real involved calculus here. But if we had a value that was just beyond 0, what are our points going to look like? Where are we going to have values? So I'm saying like, what if x was 0.1? So then we'd have y equals 1 divided by 0.1. What is that? What value is that? 1 divided by 0.1? Well, 0.1 is 1 out of 10, so the reciprocal of that would be 10 over 1. So that would be 10, is that right? So here's 1. So a tenth would be 10, so something really large. If x was 100th, you would understand that that yields a y value of 100. So as we draw closer, this is going way to infinity. And as we get closer to 1, okay, if x equals 0.99, right, then this is y is 1 over 0.99, which is almost 1, right? It's just barely, okay, so, right, it's almost 1 divided by 1. 1 divided by 0.99. Okay, so it's 1.001. Okay, so whereas this is going to be 1 here. So if x is 0.999, it's just going to be just above 1. What if x was 1? Well, if x was 1, we would have y equals 1. And what if x was 2? Then we have y equals 1 over 2 as a half. So you see what's going on here, right? So yeah, so what's happening is that this graph is coming from positive infinity, and it's coming down. It's hitting y equals 1 here, and then it's going down. And as x gets larger, we have 1 over very large numbers, which is approaching 0, right? Okay, so the vertical asymptote is here. We could use the same logic to find out what's happening right around here, and you would find out that we're coming from negative infinity, oops, and then hitting y equals negative 1 over here. Let me draw that again. Okay. Okay. Now, is there an x-intercept? What value for x will make y equal to 0? Not 0, not 1, not negative 1, not... Well, the answer is there is no x-intercept, right? So it kind of looks like that. Okay. So vertical asymptotes, you're right. The restriction on x causes the denominator to be 0. That's no good. How can you check this? Basically, you can use test points and find out where the values are. Okay? Nothing really big and scary. Pretty basic there. Okay, let's recall something that we learned earlier, though. Do you remember, if we're talking about rational functions and we were talking about limits, remember in chapter 1, I think it was 1.3, but if we had, let's say, x squared minus 4 over x plus 2, okay? You look at this and you say, hey, Mr. Maxwell, I see that x is in the denominator, and so we have a problem at x equals negative 2. X cannot equal negative 2 because that yields a value for y that's undefined. That makes it 0 down here. But do you remember what we did with this particular rational function? What did we do? Okay, factored the top, and we tried to simplify. So this is x plus 2 times x minus 2. It's a difference of squares. And so if we see that as a difference of squares, well, now you can say, hey, this actually simplifies down, and this binomial here in the denominator, it divides out with 1 in the numerator. And so this actually simplifies down to this, x minus 2, which is simply a line, right, that travels through x equals 2 and y equals negative 2, right? So it looks like this. Except what did we realize? Back up here, what does this all mean? What did that represent in chapter 1? The hole. Yeah, the hole. It was a gap discontinuity. So here we go. At negative 2, we had a gap. Now, is this a vertical asymptote? No. Okay, this is different than a vertical asymptote. So if this restriction in the denominator can be factored out, we have to think back to chapter 1 and say, hey, that's not a vertical asymptote. This is a vertical asymptote here, okay, where we have definitely something that's undefined, and the graph behaves sort of differently than with a gap, right? Because this is exactly like a line, except for this one little point, there's no value, and then it just skips over it. So this is a gap discontinuity that we learned in chapter 1, okay? All right, so we have to remember that. We have to remember that. What about this now? 1 over x squared. What if we took a look at another simple rational function that does have an asymptote, and we looked at that? Well, just to save some time, okay, we know that at x equals 0, we're going to have an asymptote, because that x cannot be simplified out of there. So we're going to have an asymptote there. And this is squared, right? So that means that y is always positive no matter what. It's positive. Even if I had a negative x value, all right? So even if I took like negative 0.2 or something, right? 1 over, negative 0.2, right? That's 1 out of 5, right? Okay. So 1 divided by 0.2 would be 5. Squared is 25, but it's positive. So it's really up here, same as positive 0.2. So what you end up having then is you have, okay, there's 1, there's negative 1, and positive 1. You have this same sort of thing happening, but they both kind of head towards positive infinity. They're both positive. And that should be symmetrical. Okay. And I think you actually see that one in your textbook somewhere. That exact 1 over x squared. Yeah, actually on page 207 there. Okay. So, any questions on vertical asymptotes? Yeah, the question being, if there's a vertical asymptote, is there always a horizontal one? You could have graphs that look really funny. You could have graphs that have a vertical asymptote, okay, and they could kind of look like this, all right, and then kind of like this, and that does not have a vertical asymptote. It has something called a slant asymptote, which we're going to learn about here shortly. Okay, so not necessarily horizontal. You could have other asymptotes, but I mean, I guess conceivably you could have, you could have multiple vertical asymptotes, and then you could have, just really weird things happening too, right? So not